favors SN2, as well as some applications, right? So before we start, let's try to attempt the true-false questions, right? For the third option, can you change the nucleophile to electrophile and electrophilic to nucleophilic? let's go through. Right. After I finish this summary, then we'll see whether your answers are right. So structure-wise, this one nothing much. It's more or less similar concept to your alkanes that I've learned, primary, secondary, and tertiary. Right. So physical properties, boiling points higher than alkanes, because now you have permanent dipole interaction on top of your ID. Solubility wise is insoluble in water but soluble in organic solvents like ethanol. So most of the time, so sometimes your halogenal alkanes can be used as solvents, for example your chloroform. Right. What's the formula of chloroform? CHCl3. Okay, this is used as a solvent, right? And if you go watch those kind of dramas, right, people usually, kidnap some people, so they'll put chloroform into a handkerchief. So after you smell, you'll just faint. It's also this thing. But they're all quite good solvents. Another solvent that you usually use is dichloromethane, right? Or short form DCM. So based on this name, you know that it is CH2Cl2. This is also used as a solvent. And of course you have your nonpolar solvent CCl4, which is your carbon tetrachloride. So all of these are used as solvents, and they all have slightly different properties, right? For example, your carbon tetrachloride, it's non-polar, or the rest are polar, right? So they usually we usually use them to dissolve organic compounds that we synthesize, right? So for density wise, density increase in the order RCl smaller than RBr, smaller than Ri. This is quite obvious because Ri is the heaviest, right? And although Ri has a larger size than your RBr and your RCl, the increase in mass overwhelms the increase in volume. So that's why you have higher density for Ri, right? All these are quite trivial. So some reactivities of halogenal alkenes, you can see from the table that their CX bond length increases down the group. Of course, the strength will decrease down the group, and their dipole moment actually decrease down the group because it gets less and less polar. So all CX bonds are polar due to the electronegativity difference between C and X. So this means that halogen withdraws electron density via induction, leaving the carbon with a partial positive charge and electrophilic in nature. So if you have a CX bond, you can draw a delta plus here and a delta minus here because this bond is polarized due to X, right? So this polarization is actually what makes your Rx reactive, and that's what makes your Rx react in this way, right? So in addition, the halide that is kicked out is also quite stable. Why do I say halides are stable? Now, HCl, HBr, and HI, right? We have learned that all of them are quite strong acids. So which one is the strongest acid of these three? HI is the strongest acid, right? So why is HI the strongest acid? When we compare acidity, I believe you all have done alcohol chapter, correct? You all have learned how to compare acidity. So for acidity, we first, deprotonate them. In other words, minus H plus. So we have a Cl minus, we have a Br minus, we have I minus. And then we just have to compare the stability of this, right? So the most stable ion would mean that the HX of that species will be the most acidic, since it prefers to lose H the most, right? So why is I minus most stable? Is because if you look at I minus, right, it's the biggest and you have a single minus charge, compared to, let's say, Cl, which is smaller and you have a negative charge. For this, the charge is dispersed over a larger volume, compared to this, which is dispersed over a smaller volume, right? This is, do you find this similar to your resonance concept? right? If let's say you have a negative charge here and it's dispersed over a large volume, it's stable compared to something, for example, this thing, which you cannot delocalize and disperse, which will be less stable. So it's the same concept, right? Another way you can explain it is that comparing all these bond energies, Hi bond is the easiest to break. So obviously, it will be the most acidic, right? This is another way that you can compare. So there are two ways, right? So although the trend increases in this way, right, all of these three are more or less stronger acids than other species, right? This is because all these three are relatively stable. So that's why halogenoalkanes are quite reactive towards SN1 and SN2 reactions, right? So from the above, you can deduce that stronger CX bond will translate to a slower reaction. Therefore, the rate of substitution will follow the order, no matter if it's SN1 or SN2. Because for either SN1 or SN2, you involve the breaking of your CX bond, right? So we can't really use this to determine whether you undergo SN1 or SN2. And there are other more important factors we can check, right? So let's talk about SN2 first. So I've already shown you the mechanism here. So for SN2, you can see that for general nucleophile attacking this RX species, but take note, X doesn't have to be halogen. Basically, remember what I said just now, the leaving group ability, which one is more stable? As long as X can leave as a stable group, SN1 or SN2 can occur, right? X need not be halogen. And that's why a lot of students stumble. They always look for halogens before they think that, oh, then my nucleophile substitution can occur. But just take note, X doesn't have to be halogen. And your nucleophilic substitution is not defined in terms of your halogenal derivative, right? It's something like, okay, this reaction is called nucleophilic substitution. Halogenal derivatives can undergo nucleophilic substitution. Maybe some other things can undergo substitution. Maybe alcohol can undergo nucleophilic substitution. You're just learning this as one example, right? So the concept is actually how you draw the mechanism and identifying which one is the nucleophile, which one is the X, right? So first, the nucleophile will attack the RX from the backside, forming a C-new bond and breaking a CX bond simultaneously to give a pentavalent transition state. Take note, this is a pentavalent transition state. It's not a pentavalent intermediate, right? So transition state is the top of the mountain, while for intermediate, right, is a valley between the two states. So there's a difference between these two, right? And of course, I already told you the answer to example 1 actually, right? So you can just fill in the example 1 with these two graphs. So this is your SN2, this is your SN1, right? So for your SN2, this is the transition state. For SN1, this is the intermediate I, right? You can go ahead and label all your EA delta H, right? So you can see that for SN2, this is a transition state. There's no way for you to isolate it. But for this intermediate, you can actually observe it using different spectroscopic techniques, right? So another point to note, for SN1, although I say that there's an intermediate, doesn't mean there's no transition state. There's also transition state, which is this point and this point, right? So for example, let's say this transition state, right? How does this transition state looks like if we know that this transition state looks like this? So since we know that for SN1 reaction, this bond has to break, right? This one has to break, which means the transition state will be the state whereby this bond is only partially broken, which means this one should resemble this structure. Take note, this bond angle, right, becomes larger because as it breaks, originally it's like that, it becomes more and more planar, right? So the transition state will be something like this. Doesn't mean this one doesn't have, but this one also have. Just that the intermediate is more interesting than transition state, right? So just take note, most of your reactions all of your reactions should have a transition state because all of them needs activation energy, right? Just that whether we are interested to know the transition state or not is another thing, right? So anyways, going back to this. So since the slow step involves both species, the rate equation can be expressed as the following, right? So this is quite standard. So now the question is, why is the first step slow? Any ideas? Remember, you need energy to break your CX bond, correct? So when you input energy, when you break your CX bond, you need to input energy. This process will be slow, right? Compared to, for example, your SN1 second step, right? Whereby you form a bond. Another thing is, look at the pentavalent transition state, right? Originally, you have 4 things connected to your carbon, but at your pentavalent transition state, you have 5 things. So there's an increase in your steric hindrance. So that's why it's quite unfavorable as well. So that's why you will need to input energy, and this input of energy translates to a slow step, right? Because you need time to absorb that amount of energy before reaction can occur. So that's why your SN2 proceeds in this way, right? Next, for SN1. For SN1, the first step involves the hydrolytic cleavage of your CX bond. So after this hydrolytic cleavage, you will generate this carbocation which is planar, right? And your positive charge lies in your unhybridized p orbital. So the next step involves the nucleophile attacking your carbocation, but it can do so from either side, the above or below, right? So attacking on the 2 sides will result in a race-mate mixture, right? Because there's no way for you to control whether you attack from the top or below. So that's why you'll have a race-mate mixture. So since the slow step involves only the Rx, the rate equation can be expressed as the following, right? So later on you'll see what's the significance of the 2 rate equations, right? So the next column, something related to your SPA, right? So how do you determine whether a given Rx will undergo SN1 or SN2? For example, you know quite straightforward that primary will undergo SN2, tertiary will undergo SN1, right? What if I give you these species? And then let's say I give you a nucleophile NaOH, right? And then I want you to determine whether you undergo SN1 or SN2. What should you do?
See whether it will depolarize.
I'm waiting for the answer, right? But take note, is this chiral? This is not chiral, right? So even if it's SN1 or SN2, my product won't rotate plane polarized, because this carbon, these 2 groups are the same, right? That answer is only applicable if, let's say, I have something like this, right, whereby it's chiral. Then I know whether you will rotate plane polarized light or not, right? So for now, I cannot use the plane polarized thing to determine whether it's SN1 or SN2, right? So now, what other ways can I use to determine whether it's SN1 or SN2? This is something related to your kinetics, that's the hint. Look at your rate equations, right? How do you determine? So if it's an SN2, rate will be equivalent to Rx times nucleophile. If it's an SN1 reaction, rate will be equivalent to K times Rx, correct? So what's the difference between these 2? It's the nucleophile, correct? So I can just start off with some concentration, for example 0.1 mole per dm cube, right? And then I double it, and then I see what happens to my rate. If my rate gets doubled, it's quite obvious that it's an SN2, correct? If rate doesn't change, you will be an SN1. It's that simple, right? So you can further elaborate your answer by saying that, oh, I can perform 5 sets of experiment, and then after that I plot a graph of rate, which is 1 over T using your stopwatch, against your concentration of NaOH, and then I see whether is it a straight line right? If it's a straight line, then I know it's SN2. If it's a flat line, I know it's an SN1, right? Just that this one is more accurate. And using this graph, you can also determine what is K, isn't it? Okay, so like what I said, SN1 and SN2 are not exclusive to halogenal alkanes only. Other reagents such as alcohols can also undergo such mechanism, right? In fact, for your inorganic chemistry, right, SN1 and SN2 can also occur, right? I was telling him yesterday that if you put SiCl4 in water, right, you will get SiO2. So how did this reaction proceed? So same thing, these two can undergo something like a SN1 or SN2 reaction, right? That's not the main point. The main point is you will get this intermediate, right? Something like your SN2 or SN1 reaction. And then what happens is dehydration will follow, whereby this water is kicked out and this water is kicked out, right? So as you kick out these two water, this point will come down here to form a double bond with the O. This point will come down here to form a double bond with the O. So therefore you get SiO2, right? So this is not even organic, this is inorganic, and SN1, SN2 also applies, right? So you can go back and relook at your periodicity and see and try to understand how these reactions proceed via the mechanistic way, right? So the next section is quite important, determining which mechanism predominates. So there are 4 factors that could influence the mechanistic pathway that a reagent can undergo, and you should always consider these to determine if a particular starting material undergoes SN1 or SN2, right? So first one is your substrate, which is your degree of substitution, right? For SN2, the nucleophile must approach the carbon center amidst the other groups, therefore steric hindrance plays an important role. So primary Rx will display the lowest amount of steric hindrance to the incoming nucleophile, hence encourage your SN2, right? Because everything occurs in one step, so the least hindered substrate will prefer to undergo SN2 the fastest. So that's why the trend is like this, right? But for SN1, the nucleophile does not attack the carbon center directly, but only do so after your leaving group has left. So therefore, steric effect doesn't really play that much of a role, right? And somehow your carbocation that is formed is planar. It's always planar. So nucleophile can always come from the top or from the bottom. So there's not so much of a steric hindrance to begin with, right? However, if there are more R groups bonded to the carbocation, it will be more stable. So therefore, a tertiary Rx will display the greatest amount of carbocation stability and hence encourage your SN1 reactions, right? We always say carbocations are stable because of electron donating groups, right? But what actually stabilizes the carbocation? For example, like this case. These are carbocation, correct? So last time, remember, we talked about this one, question 1b of your the behind part, right? We talk about this example, whereby there's an oxygen connected to R group, right? And then I told you that there's a lone pair here, right? Which can be donated to this orbital to stabilize it, right? Remember the example 1b, right? So this stabilization actually encourages your SN1. Now if you were to look at your carbocation, which is like that, take note that this CH is actually a sigma bond, and there's also a electron pair in it, correct? So the same effect can occur by stabilization, but this effect is weaker than this effect, because for this bond, your bond pair is stuck between C and H, but for this lone pair, it can datively bond to this. So this lone pair is more available to donate and stabilize this than this bond pair, although this can still stabilize it, right? So that's why for this there's stabilization, interactions. And take note, you have 1, 2, 3, 4, 5, 6, 7, 8, 9 CH bonds which can do so. So the overall effect makes this very, very stable compared to your primary and your secondary, whereby there's less CH interaction with this, right? So that is actually what stabilizes your carbocation, and that's why we always call this electron donating groups, right? This is where the donating effect comes from. I bet none of your teachers tell you this, right? And this effect, this is just for information, it's called hyperconjugation, right? While this example they have went through before is called conjugation. It's called hyper because it's from a sigma bond. It's not from the lone pair, right? So if you're interested, you can just go Google about it. This is just for info to explain why it's electron donating. So if you look at the graph below, right, it summarizes the substrate effect. For SN2, primary will be the fastest. For SN1, tertiary will be the fastest. And for secondary, it's somewhere in between, right? But usually for secondary, it's SN2, right? That's usually, doesn't mean all the time, right? So next factor. So you can see the for info, a secondary RX can proceed via either mechanism. So you should consider other factors before you determine whether it's SN1 or SN2. This is just for info, right? So first factor we already talked about, right? Second factor, nucleophile. Recall that the rate of SN2 depends on the concentration of a nucleophile, while the rate of SN1 do not. Therefore, it is intuitive to say that a stronger nucleophile will encourage SN2, while a weaker nucleophile will discourage SN2, and thereby favors SN1. Okay, doesn't mean weak nucleophiles favors SN1. Just take note. Weak nucleophiles disfavors SN2. If you disfavor it, that means SN1 will be faster, right? In fact, if you were to analyze it in a kinetics way, right? Shouldn't draw this way. I should draw it this way. RY, right? So if you throw in a nucleophile, it can either proceed via SN1 or SN2. So for primary RX, SN2 will be fast, SN1 will be slow. Therefore, we usually ignore SN1. And for tertiary is the reverse, right? So this is what it means. So since SN2, for example, we use a secondary RX, right? Secondary RX. We don't know which reaction path you will undergo, but we know that if you would use a strong nucleophile, SN2 will be fast, this will be slow, right? And if we use a poor nucleophile, this step will be slower, right? If this is slower, of course, majority will undergo SN1. So we are looking at the relative rate of these two reactions, right? Not really absolutely fast or absolutely slow, right? So therefore, I really gathered all these nucleophiles and put it in a table form, so you can see which are the strong nucleophiles and which are the weak nucleophiles, right? So for example, if let's say I have a secondary halogenoalkane, those strong ones will favor SN2 and those weak ones will favor SN1, right? So for example, this reagent, this substrate, and then I throw in RO minus, or something like that, right? If I throw in RO minus, you know that you undergo SN2 because it's a strong nucleophile, right? So you know that it will lead to the inverted product because SN2 will lead to inversion. So now you can predict what is the product as well as its stereochemistry. Now if let's say I were to throw in H2O, which is a weak nucleophile, you'll know that I'll end up with a racemic mixture, right? You can use the wiggly lines to indicate that you get both products. So this is why it's useful, right? So therefore for SN1 reaction, using either OH minus or H2O would give equal rates despite OH minus being a stronger nucleophile, right? This means that if let's say I have this tertiary RCl, right? You know that I can throw in NaOH to allow SN1 to occur, right? But I can also throw in H2O for SN1 to occur, right? And for both of these, the rate is surprisingly the same, even though OH minus is a stronger nucleophile than H2O, right? Why is this a stronger nucleophile? It's because OH minus is negatively charged, while for your H2O, it is neutral, right? So the reaction of this with your this species will be faster. So that's why for SN1 reactions, if you can use H2O, then why you use NaOH when H2O is virtually everywhere, right? So you can actually, this is actually the same concept as your example 2, right? Whereby SN1 reactions is not really affected by what nucleophile you use, if let's say both of them can give you the same product, right? So although this is important, example 3 is even more important, right? So can you try example 3? Maybe you can underline the species, right? So for the first one, ammonia versus water. So if you draw ammonia and water, this is what you get. Recall the definition of a nucleophile, right? A nucleophile is a species which is electron rich, and you will donate electron density away, right? So now we just have to compare which one would prefer to donate its lone pair away, right? Comparing nitrogen and oxygen, which one is more electronegative?
Nitrogen. Nitrogen.
More electronegative. Oxygen, right? FON, that's how your trend of electronegativity looks like. So therefore, since oxygen is more electronegative, it is intuitive to think that O will not like to donate its lone pair away. So since it doesn't like to donate its lone pair away, it will be less nucleophilic, right? So NH3 will be more nucleophilic. So the concept of this you can put behind it's about electronegativity. Right, that's the concept. These two are only examples, right? Next, H2O versus H2S. Right, in fact, for all of these four, they involve different concepts. Right, this is the first concept. For the second one, O and S. If you were to use the same concept, right? If you use the same concept, you will think that, oh, this one which is less electronegative should be more nucleophilic, correct? Well, that's only true for this case, but for this, we will prefer to use size instead of electronegativity, right? Because O and S are from the same group, so we don't really compare electronegativity for atoms with different size. So the concept for this is size. So what the size tells us? It tells us that this lone pair which resides in a higher energy orbital, right? Why is it higher energy? Remember, for O, this O is actually sp3 hybridized, correct? For this P, is what P? 1P, 2P, or 3P? This P is how many P? 2P, right? For this sulfur, it's also sp3 hybridized, but it's 3P. You have learned that 3P is higher energy than 2P, of course, right? Since this lone pair is of higher energy, it's intuitive to think that, oh, it will be easier for it to donate because it's more reactive since it's higher energy, right? Again, it's related to size because higher p orbital means larger size, right? So this teaches us a lesson. The lesson is, if they are from the same period, right, we'll look at electronegativity. If they are from the same group, we'll look at size. That's the dominating effect, right? That's the second concept. For the third one, RCH2O and RCOO minus. If you were to draw out the two structures, right, one of it is like that, the other one is like that. We can't use electronegativity because both are oxygen. We can't use size as well, right, because both are oxygen. So now we have to use resonance to explain, right? So what about resonance? For this negative charge, it's actually delocalized within this system, right? So you can draw this structure like that if you want, right, to show that the negative charge is dispersed between these atoms, right? So this is dispersed, but for this is not dispersed, right? You can say that this is delocalized, or for the first one it is localized. You know that delocalizing stabilizes the negative charge, while localizing destabilizes the negative charge. So if it's unstable, it will be more reactive. So this one will be a stronger nucleophile, right? Another way you can think about it is that for delocalization, your negative charge is dispersed, so it's not as nucleophilic as a species whereby its negative charge is forever on one atom, right? So the concept here now is resonance. And lastly, the last example, right? You have this versus this. Right. So can you tell me, this negative charge resides in a what orbital? By the way, we can't use these two, electronegativity and size, because both are carbon, and there are no resonance structures possible for these two. So therefore, we cannot use the above three. So for this case, the negative charge lies in a what orbital? This is what orbital? This is your sp orbital, right? And then for this, it lies in your sp2 orbital. Just imagine originally, how do you get this species, right? Originally you have this species, and then you just remove the H+. That's how you get this species, right? In other words, originally the lone pair which is here, originally the bond pair which is here, becomes this negative charge, right? The orbital which it was at remains the same. So this is sp hybridized, this is sp2 hybridized, right? So what if this sp, this sp2? Which one will be more available? sp negative charge or sp2 negative charge? Which one has got greater S character? SP, right? So what if it has a greater S character? You'll be closer to a nucleus, correct? So if it's closer to a nucleus, we know that nucleus is positive, right? The closer it is to a nucleus, the stronger the attraction or the weaker the attraction. Comparing this to this, which attraction is stronger? Of course, this attraction is stronger compared to this, whereby it's weaker, right? Which means which one will be more available? Which negative charge will be more available? SP or SP2? It will be SP2, quite obvious, because it's less attracted to a positive nucleus, correct? Which means the second species will be more nucleophilic. Right? So I'll call this effect orbital effect. In fact, ABCD, right? I call it the ARIO effect, right? In fact, this ARIO effect, you will meet it again in the chapter of alcohols, right? In fact, this ARIO is very, very, very useful. You can use this to explain acidity, basicity, nucleophilicity, electrophilicity, right? With this ARIO, you can forget about what your teacher has told you, because this has so far has never failed, right? So now it's just a very, very brief intro of this ARIO. We'll meet it again next time, right? So this is compare nucleophilicity. Next time we see it, you'll be using it to compare acidity, right? So next, leaving group stability. The third point, both SN1 and SN2 reactions are sensitive to a leaving group stability because both of them will involve the loss of a leaving group. So if the leaving group is bad, then neither mechanism can operate, right? So if you were to look at the cartoon, leaving group ability is how willing your cat that's originally in the basket wants to leave. If it's very, very willing to leave, then everything will go very smoothly. The transfer will be very, very fast. But if it's very, very reluctant to move, then the rate will be very, very slow, right? No matter if it's SN1 or SN2, you see that the cat still need to leave. So we can't really use leaving group stability to determine whether you undergo SN1 or SN2, right? But nevertheless, it will tell us the rate. For example, if I compare two SN2 reactions, I can use leaving group stability to compare which one will be faster, right? So once again, I've already given you the leaving group ability here. So on the left side you have poor leaving groups, on the right side you have stable leaving groups, right? Now let's just quickly explore. For the halides, we already explained why they are stable, right? Same thing for water. If water can leave, it's also very stable because water is neutral, right? And the center group, you have a sulfur species, is also very stable because the product can be resonance stabilized if you want to draw your resonance structures, right? So again, right, this is something like your carboxylate, which we have talked about just now, right? You can delocalize, and this actually stabilizes your anion, right? So this is how you draw the resonance structures and so on, right? So this is leaving group stability, and for those poor leaving groups, you see that we have a NH2 minus, right? Which is quite unstable because seldom you will see this NH2 minus species, precisely because it prefers to form NH3 instead, right? Ammonia is the most stable form, and Now if you were to see this reaction, you're actually trying to remove H plus from NH3 to form this NH2 minus. You know that NH3 is a base. Now you're forcing it to become acid, so that's why this species is very, very unfavorable. That's why the backward reaction to form this thing is more favorable. So that's why it's a poor leaving group. Same thing for your hydroxide as well as your RO minus, right? Now the significance of this is that if let's say you have this species RCl and you throw in OH minus, you can get this species. Okay? But, sorry, I don't use OH minus, I use a more generic one. NU, right? You have this RNU. But if you were to take this and throw in nucleophile, nothing will happen. Because OH, remember, is a poor leaving group. If it's a poor leaving group, this doesn't like to leave. So no matter how strong a nucleophile is, the cat is reluctant to leave the basket. Right? So that's why it is significant. Right? So now let's try example 4. Me is metal, right? Me is metal, TS is just this group, this area group, right? That's TS, abbreviation. Sorry, this is TSO, right? This is TSO, not TS. Why not you just circle the group which will be substituted, right? So you don't have to redraw. So for the first one, which one should be the one that's substituted? BR, right? Take note, you are using an equivalent amount. That means you are only adding one equivalent. right? 1 equivalent means to 1 mole of your substrate, you only add 1 mole of your reagent. Because you want to perform reactions selectively, you don't want everything to react. Okay? So the concept, first thing, when you look at H2O, you know that it's a weak nucleophile. A weak nucleophile will encourage SN1. So you automatically cancel all those primary sites. Right? So once you cancel all those primary sites, you'll be left with 2 options. One is the Cl, the tertiary Cl, one is the tertiary bromine. Right? So out of these 2, which one is the better leaving group? You will be Br minus. Like what I mentioned just now, right? So that means if you throw in H2O, you will preferentially substitute away the Br. Okay, so there's only one Br which is substituted. Next, NaOH. NaOH is a strong nucleophile. You can always refer to the table, right? So you prefer to undergo SN2. So you eliminate all those primary tertiary sites. So now you are left with Cl being the leaving group, TSO as well as OMe, right? OMe is the same as OR. So OR is a poor leaving group. So now if you want to compare TSO with Cl, Cl is a more stable leaving group, right? So therefore NaOH will substitute the Cl, the primary Cl. So there's actually quite a lot of things to consider when you look at SN1, SN2 reactions, right? And this is why your leaving group stability as well as your nucleophilicity is important, right? This is just one of the applications. And lastly is your solvent effect, right? Surprisingly, this was once tested, right? Although it's FYI, but the concept is quite simple to understand, right? So the choice of solvents can have a profound effect on rates of SN1, SN2 reactions. Polar protic solvents encourage SN1 while polar aprotic solvents encourages SN2. So polar protic solvents contain at least one hydrogen atom connected to an electronegative atom, right? So for example, your HF, HO, all these are protic acids because they contain, protic means proton, right? So they contains a proton connected to an electronegative atom, right? All these are protic acids. Polar aprotic solvents means the opposite. You don't have a proton connected to an electronegative element. For example, solvents such as this. There's no such thing, right? Another way you can phrase it is that polar protic solvents can form hydrogen bonds, aprotic solvents cannot form, right? And take note, it's called a polar aprotic solvent. So this is not a polar aprotic solvent because it's not polar to begin with. This is just a non-polar. Sorry, this cannot be a solvent because it's a gas, right? For example, this hexane, right, is called a non-polar solvent, right? So basically you have 2 categories, polar protic and polar aprotic. So let's try to understand why they favor each other, so favor different reactions, right? So now recall that for your SN1 reaction, you generate a carbocation, right? So if you generate this carbocation, how do you stabilize it? You can use negative things to stabilize this positive charge, right? Which means as long as you have some atom with a lone pair, you can stabilize it. So it doesn't really matter what is the other part. So it can be a polar aprotic solvent which stabilizes it, or a polar protic solvent that stabilizes it, because what is actually stabilizing this positive charge is this lone pair. So it doesn't really matter. But for SN2 reaction, right? Remember for SN2, right? For SN2 reaction, what's actually happening is your nucleophile that is actually doing the attack. Okay? It's doing the attack, right? So now just imagine if you were to throw in this polar aprotic solvent, which is the one without proton, nothing will really occur because there's no positive places for you to solve it. right? So if you use this solvent, nothing will occur. But if you use a polar protic solvent, right, they know that this is negatively charged, and there is delta plus, delta minus on your water. So this can actually solvate your nucleophile. So you can imagine that there's a lot of water molecules. I use this to represent water surrounding our nucleophile, right? So as to solvate your nucleophile. Since rate of your SN2 is equal to K times concentration of your Rx times your nucleophile, by solvating nucleophile, you're actually making nucleophile less available. So that's why your SN2 rate will be decreased if you use a polar protic solvent. So if you disfavor your SN2, that means SN1 will be more likely, right? Which means for your SN1, you'll be favored by protic solvent. And for your SN2, you'll be favored by aprotic solvent, because by using aprotic solvent, you can't solvate this, right? So that's actually the concept behind it. So if you were to turn to the behind, you will see that there's one prelim question which asks such things, right? So you can turn to the back, try to attempt that question. Let me see which one. Question 18, 1-8, right? So for question for A, there's a few ways, correct? What do you use to determine, to differentiate these two? PCl5, right? Because PCl5 will react with the alcohol. And what observations will you see? Yes, white fumes of HCl. And you used?
Sodium metal.
Yeah, if you use sodium metal, you will have H2 generated effervescence, right? So I believe that there's more than one way. You can use SOCl2 as well. Another way you can do it is, you can remember the way to precipitate Cl, hydrolysis followed by AgNO3. You'll see white precipitate, that one also can, right? So there are numerous ways. And then for B, what will be the rate equation? Is it SN1 or SN2? SN2, correct? Basically, it's quite straightforward as well, right? So order with respect to either one is 1, and the rate equation will be rate equals K times concentration of both, right? So the next one is the solvent effect, which I was talking about. So which one is the nucleophile?
Oxygen.
You sure it's the oxygen? Why is it being substituted?
Like the OH group.
It's not the OH, it's the Cl. You have this thing, afterwards you get this, correct? So this must be a nucleophile that you have added such that you have this reaction occurring, correct? Like what I said, the nucleophile can be basically anything. It doesn't have to be what you have learned before, for example OH minus and NH3, right? As long as it's a negative charge species, and if it's a good nucleophile enough, it can act as a nucleophile, right? And take note, the nucleophile is not CH3S Na, it's CH3S minus. The question even says so, right? State the ion. And next they ask you to explain why DMSO does not solvate anions effectively. Right, this is exactly what I told you just now. Right, there's no delta plus for you to solvate this between these two species. Right, this is in fact similar to a DMSO, just that I'm changing this to sulfur. So since there's a lone pair here and this negative charge, there's no way for you to form lone pair charge interaction, right? Because this is negative, this is negative. Another way you can think about it is this is partial negative, this is negative. There's no way for you to solve each other. So therefore it doesn't solve anions effectively, right? So the answer is just that the lone pair oxygen, okay, does not interact with the negative charge anion. So there's no interaction, right? No interaction means no solvation. Another way you can explain is by saying that SO bond is polar, such that you have a delta minus on O, right? So same thing, the delta minus doesn't interact with the negative charge, so therefore doesn't solve it well, right? Either ways is fine. But the important thing is you have to recognize that this is negatively charged or has a pair of lone pairs, right? So part 4. This is again what I explained, right? So if you carry it out in ethanol, which is a protic solvent, is as good as saying water, right? So for water, there will be ion dipole interaction because now you have a delta plus and you have a minus. So such interaction will solvate your nucleophile. So your nucleophile is less available to perform your SN2, that's why the rate is lower. Right? Alright. If you understand the part in my notes, this part shouldn't have a problem. Okay, I repeat. Since ethanol is a protic solvent, right, the delta plus on the hydrogen can solvate anion via ion dipole interaction. So since nucleophile is solvated, it's less available for the attached SN2 rate decrease, right? Okay, we might as well do the last question, part D. Actually, sometimes can be quite biased because all of these concepts they have told you, if you do H3 chemistry, you should all have dealt with these before already, right? Because all of this was learned, including D, right? Such reaction is already learned by them already, so it's a bit unfair. So for the first step, I already told you it's acid-base reaction, so it's quite standard for acid-base reaction, right? The mechanism will be just like that. Okay, you have to draw the delta plus and the delta minus. Such a mechanism is very standard for your acid-base reactions. So you generate these species, right? Afterwards, they told you that the second step involves an intramolecular reaction and it's rate determining. Since this reaction is about nucleophile substitution, you will know that this, which is a nucleophile, is present, and this is a leaving group, which is also present, right? So therefore, an SN2 reaction can occur, whereby these will come in, and your Cl will be kicked out, and you will form this epoxide, right, which we have seen before. So this is your compound W, right? H. Somehow it says that it's an intramolecular reaction, so there's not much of a variety, right? This is like the only thing that can occur. So this is actually an SN2 reaction, right? If you wish. So you can imagine this to be the same as your Cl. You have a H here, H, and you have a OH coming in to do the attack. It's analogous, right? So that's why I say don't just memorize the reactions, right? Understand why they occur. So let's go back. That's your solvent effect. So anyways, those that are important I already mentioned already. Those that are less important, I already bracket and put it as FYI, right? So it's just for enrichment purposes. So as a summary, I already placed these two reactions side by side as in the table form. So you can see that their rate equations differ. The rate depends on different factors. So the concept for SN2 is steric, SN1 is carbocation stability. SN2 wise, you will have an inversion product, SN1 you will have a race meet product, right? And the energy profile is also described there, so you can go ahead and see it. So let's try example 5, right? Do you agree? Like what I told you just now, OH minus is a poor leaving group, correct? So it's very reluctant to leave your substrate, so that's why A cannot occur. While for B, you're actually converting it to a good leaving group, right? So therefore, root B will occur more preferably, right? So this teaches you another thing, is that you can actually convert your poor leaving group into a good leaving group, right? So for example, if let's say you want to obtain this product, right? This is your starting material. What do you think you should do to obtain this product? Instead of another method, right? Instead of using the B method, and then if I react this with acid, this is what I will generate, right? And then if you're thinking of, after I get this, right, this will become a good leaving group, and then I do this, then you're wrong, right? Recall that HCN is a weak acid, correct? So if it's a weak acid, that means this equilibrium will be favored towards this side, right? Which means this one will be a strong base. If this is a strong base, you are reacting with this, instead of doing a nucleophilate substitution, what I can do is that it can abstract this H instead. Because of course abstracting H is easier than doing the attack, because H is just so small, it's just a proton. So if you react this with this, you will not get a product, right? In fact, you'll just get this plus HCN. Okay? So it's not something you have not learned, right? It's something you have learned. Remember, how do you convert this to this? You can use PCl5, you can use PCl3, you can use SOCl2, correct? So after you convert to this, then you just have to add NaCN, isn't it? Cl is a good leaving group, correct? So there are numerous ways you can do it. You can of course convert it to bromine, iodine, whatsoever, and then perform the same reaction, right? That is the interesting part of synthesis, right? There's a lot of things you can bypass. So next, let's go ahead with the preparation of halogen alkenes. So preparation wise, first kind of preparation method is by using free radical substitution, right? So you can use UV or heat to generate your halogen alkenes from chlorine gas or bromine liquid, right? This one pretty much we have talked about it before. So for this case, right, you will have different substituted product depending on the amount of chlorine or bromine that you use, as well as which exact location you want it to be, correct? But such things is not possible to control because it's very random. So you can substitute here, you can substitute here, and it all depends on probability, statistics. Okay, so for this, it's very hard to control, and that's why it's not really preferred unless you have this case and you want to substitute here. Then there's only one place for you to substitute, so there's not so much of a side product that will be formed, right? So just take note, for halogenation of alkenes, the best thing is you only have one place to sub. Otherwise, don't use this. It's not trustworthy, right? It's not reliable. So for example, for this case, right, this will be your major product, because you have apparently six possible the probability of this place is 6, this place is 1, right? This place is 2, and this place is 3. So obviously you most likely generate this, right? You have learned this in alkanes already, so I won't talk so much. Next, electrophilic addition of hydrogen halides. This one we already learned about it already, right? You know the mechanism as well, and you know how to follow your Markov's rule, right? So if I have this, I add a HX. X will join where? Will you join here? Or here? A or B? H, huh? H will join here. Is it B, huh? Right? You will generate the Markov product, whereby the rich gets richer, right? H will always join to the place with more H. And the rate is as follows the bond energy, right? Electrophilic addition of halogens. For this, you're actually adding X2, so quite straightforward. Both of it will be X. This is to generate dihalogen compounds, dihalo compounds. Right? You can use this as a form of distinguished test as well. So next, nucleophilic substitution of alcohol with HX. For this reaction, you are using HCl or zinc Cl2, NaBr or con H2SO4, and if you want to introduce iodine, you use the last combi, right? So how do these reactions proceed? So for the first one, HCl, right? You're using this plus HCl and ZnCl2 as a catalyst, right? So in fact, you are just doing a nucleophilic, you're just doing a nucleophilic substitution, whereby you are using Cl, right, to attack here after this is protonated to generate this species. Okay, just take note, for this mechanism you can draw it in this way. First step is the protonation of this species, right, followed by your Cl minus doing the attack to form this. Okay, now you might wonder, wouldn't Cl minus remove the H plus like what your Cn did? Well, it's true, but take note, HCl is a strong acid, correct? If it's a strong acid, in fact stronger acid than your HCN. If it's a strong acid, the arrow is like that, right? If it's like that, that means if you were to throw in Cl minus, it's not likely to take H plus to form back this. So the chance of Cl minus attacking this is lesser. So therefore, this can compete with your acid base. So that's why this process can occur. But for just now, that one, it cannot occur, right? This is the concept behind it. And actually, I'm helping you do example 6, right? That's the equation anyways, the first equation, right? And for the second equation, you're actually generating your HBr in situ, right? In fact, you have this reacting with your NaBr reacts with your H2SO4, right? You will generate HBr plus your NaHSO4. So this is generated in situ before this reacts with your alcohol. Right? So probably why they don't use HBr directly, of course you can, it's probably because HBr is toxic, right? That's my guess lah. That's why you want to generate it in situ. And for the last one, you are reacting NaI with con H3PO4. You cannot use H2SO4 because if you use H2SO4, you generate HI in situ, right? But your H2SO4 will react with your HI and you will get I2. So this reaction will not proceed. So that's why you need to use a milder reducing agent, which is your H3PO4, right? So if you react NaI with H3PO4, same thing, you generate your HI plus your NaH2PO4. and these will then react with your alcohol, right? Right, so these are the main equations that are important, right? The rest is the same. So that's one way to prepare, right? And next, nucleophilic substitution of alcohol with SOCl2 or PCl5 or PX3. So you can use either combi. So for the first one, is the most convenient because reaction is clean since the side product are gases, right? So if you react your alcohol, this is example 7. If you react your alcohol with your SOCl2, you will get this plus your SO2 plus your and you plus H2, right? You can go balance yourself. So the product is very clean. And same thing for PCl5, right? And your PCl3. Let me see. I think for this you have Cl plus POCl3. For this, I seriously forgot what's the other product, right? You can go back and check what's this product, right? So for all of these, you will generate white fumes. Just take note, because you will have sorry, what am I doing? This is not H2, this is HCl, sorry. Right? For all of these products, you will generate HCl. Right? For this, maybe there's HCl somewhere. You can go back and check. Think on this one, go back and check. I forgot the equation. Right? So anyways, you will generate HCl, and you can use this to distinguish alcohol-containing species with non-alcohol-containing species. Right? So that's for your preparation of alcohol. Just think of organic chemists are the worst at balancing equations. Right? Because what they care about is what you use at the start and what is your main product. They don't really care about what's the side product. Right, so that's why my balancing so cui. Right, part 7. Reactions of your halogenal alkenes. So if you react your RX with NaOH or KOH, this one already know, right? You will have your X replaced with OH. This is the one you have learned in your notes as well. And for the next one, if you have a 1,1 dichloro product or dibromo product, right, and you react with your NaOH, what will you get? This one already learned, right? We already did the example. First, you have this, correct? Afterwards, this is unstable, and you will just lose water, and what you will get is a ketone. Right? Just think of a lot of schools don't teach this, but they test this, like the example that I told you the other time, that MCQ, right? So now the question is, if let's say I have these species, and then I throw in OH minus, what will I obtain? Yes, right? By the same logic, I'll have opposite acid. What if I have all 4X?
Just oxygen.
Oxygen, you sure?
Water.
Apart from water. Usually, organic chemists only care about the carbon-containing product, right?
Carbon dioxide.
Yes, right. So you have this. Once you have this, you lose water again. So you have a CO2 and water, right? So next, nucleophilic substitution of the nitrile formation. If you have this nitrile, if you have this RX, you can actually throw in your Cn minus to form your nitrile, right? And we call this a step-up reaction because you increase the number of carbon by 1. Right? It's quite useful. And yeah. So the conditions are as shown. If you add AgNO3, after the reaction is over, precipitation will occur, which can help you to identify the halogen, right? Same thing for the other two previously. You can actually add your AgNO3 to see which halide is present. So after you obtain the nitro product, here comes its usefulness, right? After you obtain this product, you can actually perform, there are actually three main reactions which you can undergo. First is reduction, right? So for reduction, you can either use lithium aluminum hydride or H2 nickel, right? Next time we'll see what is the difference between these two sets of reagents. In other words, the selectivity, right? So after you do this is what you get, right? Basically the trick is, this is CN, correct? Just add a H2 between them and a H2 at the end. So this is the product, right? You're merely adding H2 in between, right? So one way you can think about it is that you have a CN triple bond, just like your CC double bond, right? If you reduce your CC double bond, it's as good as saying that I introduce H2 into it. So afterwards, I just break this bond, hold hands with this H, break this bond, hold hands with this C. I'll get alkane. So for nitrile, it's the same thing, right? H will come in, the first bond break, you hold hand with this H, this bond break, hold hand with this C, and then another H come in and hold another pair of hands. So I'll have CH2 and H2, right? If you forget about this, think of the whole hand analogy, right? This is reduction, which will give you your amine. Second one is your hydrolysis, right? Acidic hydrolysis. So if you perform acidic hydrolysis, you have a COOH, right? Plus your NH4 plus. Since by right you should liberate NH3, but since it's acidic conditions, acid-base reaction occurs and you have ammonium. Another one is you use base to hydrolyze it, and take note for these hydrolysis you need to perform under reflux, right? So if you reflux it, you have ROO minus plus NH3, right? The initial product is COH plus NH3. If you were to perform it in basic conditions, your COH will be deprotonated. If you perform it in acid conditions, your ammonia will be protonated, right? Now of course you can convert from this to this and this to this by throwing in acid or base, right? So for example, this one you can throw in a base, this you can throw in acid, right? You can interconvert. Okay, huh? So just a quick question. Can I replace this with heat? Or in other words, what's the difference between reflux and heat? What's the difference between reflux and heat?
If you just heat, everything evaporates.
Then reflux?
Reflux, that's like the condensation thing.
Yes, right. Take note, reflux always occur at boiling point of your solvent, right? Just imagine if it doesn't occur at boiling point, how can it condense? Correct? So it must always occur at boiling point of solvent. But for heat, of course, it can be other temperatures. It can be lower than this, it can be higher than this, right? And of course, for reflux, you must do it in a closed system. But for heat, it need not be, right? It can be open or closed, doesn't really matter. So that's the difference. But sometimes they are used interchangeably, so just take note. Right? And next one, nucleophilic substitution of your RX is the formation of your amine. So you have to use excess con NH3 in ethanol and heat in a sealed tube, right? Like what I mentioned the other time, excess con NH3 is to prevent multiple alkylation. heat in the seal tube is to prevent your ammonia from escaping, right? So how do you draw the mechanism? If let's say it's a SN1 reaction, SN2 reaction, let's say, right? So originally you have this compound, right? I draw like that, draw the more legit way. So this is your substrate, and you have your ammonia. So the lone pair will do an attack, and your Cl will leave, right? And you will draw your pentavalent transition state. Cl H3N. Right? Take note of a delta minus. Right. Afterwards, of course, you have to indicate the slow step. Right. Afterwards, what happens is that you will generate this species, which is the inverted product. And then this is the part whereby a lot of students get wrong, right? Because some students will just, in your product, somehow the H plus will suddenly be gone by itself, right? Take note, you must indicate all of these steps clearly, right? So for this step, what happens is your Cl minus, which was kicked out, can come in to take away the H. Thereby you will form a product. That's your HCl. Right? This is the first acceptable answer. Right? The second acceptable answer is, right, once you have this, the bond pair can just come down like that to form this, right? Now both are acceptable, but why do we ignore the Cl minus? Because remember, in your solution you still have your ammonia, correct? So this ammonia can actually act as a base to remove this H. So in this solution you might have water also. So water can also come in to do the deprotonation to form the final product. So we are not really concerned with what actually do the deprotonation. So we just generally describe it as such. So somehow it's deprotonated by something which we are not concerned with, right? So either ways is acceptable, right? So depending on which one you prefer, right? So just a note, excess ammonia is necessary if you want to use primary amines, right? The seal tube is to prevent ammonia from escaping. Alkyl groups are electron donating, which results in lone pair on nitrogen being more available down the list, making the nitrogen containing compound more nucleophilic, right? This is with respect to the list here, right? So the more substituted amine competes with ammonia to attack the halogenoalkene and wins out due to its greater nucleophilicity, since there are more electron donating groups, and therefore the strength of nucleophile can be written as such. So therefore, in the presence of excess halogenoalkene or limited ammonia, polyalkylation occurs and you have a mixture of amines. So that's why you need the excess con NH3, right? And please do modify your reaction conditions if let's say you want to get the polyalkylated product, right? So please take note, the excess con, that one is optional depending on what product you want. So don't everything excess con, right? Sometimes you need limited, and sometimes the question might swap these two, correct? Like my question that I gave you just now, that I gave you the other time. So let's try example 8. So what's compound B? So it should be quite obvious, right? If you react it with excess PCl5, your 2OH should be substituted with Cl, correct? And now you have a nucleophile and you have your 2Rx at the two ends. So you can come in to do the attack on both sides, correct? So after the first attack, you will generate these species. Right? So originally it's a secondary amine. Now it becomes a tertiary amine. Some more, this reaction is intramolecular. So these two factors drives another of such of this reaction to occur. Right? So you have this, and you'll be balanced by Cl minus. And the other Cl is simply lost. Right? Because this one is the only salt that is isolated. And how do you count the number of rings? The how many member rings is just starting from this nitrogen. 1, 2, 3, 4, 5, 6. So we form a 6-member ring. Right? It's just like that. So now the question becomes, draw the structure of compound of the other structure isomer of compound A that can undergo the same reaction to give compound B. Right? So how should you do it? Instead of just now cutting these two bonds, you can just cut these two bonds, correct? Am I right? And then you just add a Cl here, add a Cl here. What's so difficult about this? Right, it's just that simple. Correct. Which means if I give you a question whereby I draw this compound and then I ask you to synthesize it, then is it that I don't know how to do already? It's just cutting the bond at the Cl, that's all. Just like what I did for this, you cut these two bonds, add Cl, this is what you get. Correct? It's just the reverse. Basically I can cut any two bonds. I can also cut these two bonds, this and this. Right? So I have a Cl, it also work. So I have 1, 2, 3 alternatives. Right? Last one will be like that. It also work. Right? There's a lot of varieties. Okay? So the next reaction, just for info, for the next set of reactions, they are all for your info, but if you have done those questions, you'll know that most of these have been tested before, so that's why I thought about them here, right? First one is known as the Williamson ether synthesis. You're actually generating an ether, right? This is the structure of your ether, ROR, right? So how do you generate this? Same thing. Remember your nucleophilate substitution reaction, right? Don't copy this first, You have OH, you have OH reacting with this, right? And you have this OH, right? Now you are just simply replacing the H with an R, and you do the attack, and this is what you get. This similar concept, correct? Just replacing H with R. Something like amine. I'm just replacing the ammonia with some other alkyl groups, and the reaction is still the same, right? So this is known as your Williamson ether synthesis, because you are synthesizing an ether, right? And you have seen this in your question before. Remember this question, OH, something like that, right? That question. That one is your Williamson ether synthesis, right? So for this Williamson ether synthesis, you can either use your RONA, which is a salt, or you can use Na in ROH. So you have learned in your alcohol that if you react this with your Na, you generate your RO minus Na plus half of your H2 gas, right? So after you obtain this reaction, it's actually quite clean, because what you get is just hydrogen gas. You can just throw this into this and you'll get ether. So this is just the mechanism, which is same as your SN2 or your SN1, right? Next one is your epoxidation, right? You have learned about epoxides as well from the questions. So how do you actually make epoxides? So this is how you can make it. If let's say you have an alkene, right? Don't copy first, understand first, right? If you throw this in, what will you get? Can you still remember? BROH, right? So BR connect to which one?
The one on the right.
This one? Correct. Marconi-Kos rule, same thing. Because the carbocation generator here will be more stable, so your OH will be joined here, right? After you obtain such a species, this is the first step. Second step, you throw in basically any suitable base, right? It can be NaOH or anything, right? So after you throw in your NaOH, what will happen? This NaOH, which is basic, will deprotonate this, right? Now you might want to argue, why wouldn't it perform a SN2 reaction? The reason is because, like what I always mention, acid-base reactions are very fast, because what is involved is just a proton, right? There is no steric hindrance or whatsoever, so this is faster than this, which is slow, right? So after this step, I won't draw this mechanism. This mechanism I assume you know, right? So step 1, you can just fill in this, right? Step 1, and then step 2 is this one, right? So after the initial deprotonation, you have this species, right? Plus your, of course, water. So what happens now is just a SN2 reaction. Remember the example, DMSO, the example, right? It's the same. So you obtain this species plus, of course, your Br minus. And this species is your epoxide. Which is again an SN2 reaction, right? So all of these you see that basically involves what you have learned, right? So they are just applications. And next is your epoxide opening reactions. So when you have an epoxide, you have learned that 3-member rings are very strained, correct? So it can in fact open up if you were to throw in a nucleophile, right? Now, if let's say you have this species, right? You know that these two bonds are polarized, so that there's a delta plus on both carbon, and of course your oxygen is the one which is delta minus. So if you throw in any general nucleophile, it can be anything, right? Ammonia, OH minus, or anything, it can react, right? So what you do is that, of course, you prefer the least synthesite, and you perform an SN2 reaction. This reaction is actually SN2, whereby nucleophile come in to attack, and the leaving group will leave at the same time, and what you will get is this species, O minus, and a nucleophile, right? And eventually, if you were to protonate it, this is what you get, OH, right? So you have seen all these reactions before in your questions, so that's why I place them here, right? Next, elimination, right? For elimination, take note the mechanism is for info, but the reaction is you must know, right? And of course, nowadays, these kind of mechanism questions are quite popular, whereby they give you the steps, step 1, step 2, step 3, and then they ask you to draw, right? You can see a lot of these kind of questions. So for elimination, you will use KOH or NaOH in ethanol, and you will heat under reflux, right? So by doing so, you will generate this product, which is an alkene. So the mechanism really given you, and take note, it's under reflux, right? So surprisingly, for this elimination reaction, there's also two kinds of mechanism known as E1 and E2, just like your SN1 and SN2. But both are just for information, right? So next, let's look at the solvent effects once again. Recall that for nucleophilic substitution to occur, you will add KOH or NaOH in aqueous solution, but for this you add it in ethanol, right? So OH minus behaves like a nucleophile in aqueous solution and a base in alcoholic medium. Substitution and elimination always compete with each other, so you need careful selection of the reagents, solvents, and temperature, which can optimize. A careful selection of the reagent, solvent, and temperature can optimize one reaction over the other. Right? You've already seen how temperature can affect, and this example shows how your solvent can affect, right? So the exact reason why elimination is preferred in ethanol solvent, right? This one is not really in your syllabus. You can go Google up on it if you wish, right? It has something again got to do with solvation effects. Okay, but it's more complicated than the solvent effect that I've talked about just now, right? So the ease of elimination is once again follows the bond length order, right? Ci bond is the weakest, so it's the easiest to eliminate, right? So compare and contrast the conditions for substitution and elimination. How do you favor one over the other, right? So for example, you can draw up a table, right? This is elimination, this is substitution, right? So for solvent wise, elimination will be favored by your ethanol, while for substitution is favored by water, which is aqueous, right? And then next is your temperature. For elimination is preferred by high temperature, while substitution is preferred by lower temperature. Doesn't mean lower, right? And what else? The next is reagent, right? Reagents for elimination, the best is you use a base. For substitution, you will use, of course, a nucleophile, right? Now, just a quick note on base versus nucleophile. NaOH, as we have learned, is a base. It's also a nucleophile, right? So if let's say you want to perform substitution reactions, in real life we tend not to use NaOH because it has both properties, and we scared that it might give us a mixture of these two, right? So most of the time we'll try to use a non-nucleophilic base if you want elimination, and we'll use a non-basic nucleophile if you want to perform substitution, right? But sometimes it's hard to control, for example like this case, right? So these are the things that differentiates substitution and elimination, right? So next, Sayzeff's rule, right? This is related to elimination. Whenever two or more alkenes are produced from elimination, the most stable one is the one with the most alkyl groups attached to a doubly bonded carbon atoms, or the more substituted product. Okay? So the most substituted product is known as the Sayzeff's product, while the less substituted product is known as the Hoffman's product. This one is just for info. So if you compare cis versus trans product will be a major due to less steric hindrance. We already talked about this in alkenes, right? So let's try example 10. Okay, what is the most stable product for the following reaction? through. Should be quite straightforward. So this Br, right? I can of course eliminate this hydrogen. And I can of course eliminate this hydrogen, right? But eliminating this hydrogen will give me the major product, right? But this is not the major product because this is the C's product. Okay, so I must rotate it such that it becomes a trans product. That's why I designed this question, because a lot of students will just draw this as a product, right? It's always the trans product that's the major. Okay? Right. It's always the trans product, right? So this is my major product. Right? It's very difficult to design questions to trap students, right? I hope you all can learn from this example to rotate your products. So next, reactivity of halogenoarenes and vinylic halides. Your school, they only teach halogenoarenes, right? So there are two effects. If let's say you have a halogen directly connected to a benzene ring, first is electronic effect, whereby the p orbital of halogen atoms overlap with the pi electron cloud. So this allows the lone pair to be delocalized. So if you see the resonance structure below, you can see that the CX bond actually have some partial double bond character, right? So since more energy is required to break this bond, therefore any nucleophile substitution will be unfavored. So it won't undergo nucleophile substitution reactions. Another thing is steric effect, right? Due to the electron-rich ring, it hinders the backside approach, because now you have to approach it in a planar way. Because if your benzene ring is here, your nucleophile also have to approach this way. So it's sterically hindered by this, right? And if let's say you attack from the top or from the bottom, it's not at the right geometry for SN2 to occur. And for SN1, you also cannot occur because the carbocation that is generated is very, very unstable. Because now you have a carbocation residing in the sp2 orbital, right? And for sp2 orbital, there's 33% s character. So remember, the greater the s character, the closer you are to the nucleus. But for now, you have two positive charge close together, so that's why it's unstable, right? So SN1, SN2 won't occur. So the same thing goes for vinylic halides, right? Same effect, whereby your lone pair can be delocalized into a double bond to form a conjugated system. So the effect is the same, right? We have seen this example as well. So therefore, halogenoarenes and vinylic halides are resistant to hydrolysis due to the above factors. And in addition, due to the electron withdrawal effect of the halogen, the benzene ring is less electron rich and less nucleophilic. Harsher conditions are required for electrophilic substitution compared to benzene, right? Now we are not looking at nucleophilic sub, we are looking at electrophilic sub, right? You have a benzene ring which can act as a nucleophile to react with electrophiles, but for now you have a halogen that pulls electron away from it. So when it pulls the electron away from it, it becomes less readily, this becomes less electron rich, so the attack of electrophiles is less available, is less ready, right? So preparation of halogenoarenes, this one I really learned about it already. If you want to prepare halogenoarenes, you just have to use the following combi, right? But take note, you have to throw in a Lewis acid catalyst, right? So you can generate your halogenoarenes, right? You of course observe decolorization because the other product is your HX, right? Whereby you have white fumes, right? Let me just finish part 12, not part 11, right? Part 11 is just for you to read yourself because it's quite got not much of chemistry things in it, right? So for 12, analysis of halogenal alkanes. Presence of halogenal alkanes can be confirmed by the following tests. Heating with NaOH. This is just your SN1 or your SN2. Before you cool the mixture and acidify with HNO3, right? Acidify with HNO3 is to prevent excess NaOH from reacting with your AgNO3, which you add later on. Afterwards, you add AgNO3 and you will have precipitation of your AgX. So different AgX have different colors and they will be formed at different rate, precisely because your Ri, right, your Ci bond is the weakest, so it's the easiest to break, so therefore it's formed immediately. And your halogenoarenes do not form anything because of what we have mentioned just now, right? Just take note for step 2, can you acidify with HCl? You can acidify with HNO3, but can you acidify with HCl? You can't, because you are trying to test for halide, yet you are trying to add halide. So it will give you a false positive test, isn't it? So you can not use HCl. Okay? So you can further differentiate this by adding ammonia, right? Because all these have different solubilities in ammonia, so you can see different observations, right? And in addition to color and rate, the mass of precipitate can also give information of the number of halides present in the compound. Right? You have more Cl, of course, the mass of AgCl would be doubled. Right? So let me quickly go through the true-false questions first with you, right? We'll be done. First question, fluoroalkanes are more reactive, which is false, because CCl bond is weaker, correct? SN2 reaction, 5 coordinated intermediate is formed, which is false, because you should form transition state, not intermediate. Right? RCN can act as electrophile in nucleophilic substitution reactions. Is it true or false? Is Cl minus a good leaving group? Cl minus is not that of a good leaving group, remember? What I told you just now? Sorry, not Cl minus, Cn minus, right? Remember the equilibrium equation that I wrote you just now? HCN is a weak acid, right? Right? They're all disappearing. It's a weak acid, right? Which means it's not likely for your Cn minus to exist because the equilibrium lies more towards HCN. So this is not stable. So this is false. Right? Using a stronger nucleophile will result in a faster SN1. Is false because rate doesn't depend on nucleophile. SN2 causes inversion, SN1 causes racemization. This is true, you know that. Tertiary RX prefer to undergo SN1. This is true as well, right? Compared to H2O, H2S encourages SN2 more, correct? H2S is stronger nucleophile, SN2 will be faster with stronger nucleophile. Following RX can be prepared using the corresponding alkane and limited Br2, which is false. You have to use excess Br2 because it's di-substituted. Following can be achieved with NAI and con H2SO4, which is false, right? Remember your H2SO4 is going to oxidize it to I2, right? SOCl2 can be used to identify alcohols. This is true. We know that there will be white fumes. Following reagent reacts with NOH to generate a ketone, which is correct. We already saw the example. The product cannot be synthesized this way, right? Because HCN is not a good electrophile, right? So it's false. Quaternary amines can be synthesized by heating aliphatic RX with excess con NH3 in ethanol in a sealed tube. This is true, right? No, this is false. Okay, because you are trying to use excess, you won't have quaternary, right? You will have mostly primary. Next, high temperature favors elimination over substitution. This is true, right? You can refer to a table. The major product of an elimination reaction will be the most substituted trans alkane. This is true as well. 2 chlorine atoms will be substituted, which is false. You only substitute the leftmost Cl because the other 2 Cls, they can delocalize, right? And lastly, you cannot use HCl, like what I mentioned. You can only use HNO3. So the last one is false. So I hope you don't fall into these traps during your MCQ questions. Okay?